Good day to everyone. Professor Brown, so I see you've taken on a new role, so let's see how this goes down. Thanks a lot for being here. I know Dr. Paul, I know Dr. Dawkins, so again, thanks for being here, and thanks to everyone for coming. It is a great pleasure for me to disperse this knowledge as such, and we're all in the same field, trying to assimilate knowledge as much as possible. So this is my...
Saying we're delighted to be here, and we're thankful to you for stepping forward to be the first one this new year. Thank you very much.
Appreciate it. So, well, let's start off. So the topic is general. It has to deal with fail-safe issues in autonomous vehicles. And a vehicle is anything that does some kind of transport, regardless of whether it's people or not. So a simple thing as a quadcopter could be an autonomous vehicle. Also, self-driving cars, robots that would carry something. All of those fall under that category. Now, let's start off with something a little dramatic. And this is how I propose to do this session. So I've done the opening remarks. We're going to look at a little dramatic video, then we look at the research problem. Dr. Dawkins, quite rightly, I tried as much as possible to put the physics in the background. Still, I'll do a little thing, just a little thing. And then we look at failsafe. I look at some black box data analysis, some real data that was collected. A proposed solution, we'll conclude, and then I'll take any questions and any comments. So, as promised, let's just look at this and see. I hope that this caption here remains when it's playing. So let's see. One second, I'm doing it.
Gracias.
Okay, so that's the video. Let me change the screen and let's share. Okay, so what we just saw there, I'm sure you understood what happened there. And that's a brand name, DJI thing, not mine. The quadcopter just flew away. It ignored control signals. It went into aircraft space. because we only allowed to fly up to 400 feet in any direction. It went into aircraft space. Luckily, nothing collided with it, or it didn't collide with anything. Then it just flipped, turned over, and of course it would head for the ground. But so far away that the owner of the vehicle would not be able to retrieve it so easily, because once it's going to crash, all video communication would also be lost. So that's the gist of the problem. It happens on brand name. Just want to make some space on the screen here. Okay, so it happens on brand name UAVs, right? Unmanned aerial vehicles. It happens on the no brand names also. And what really causes this? Now, I can't say what would cause every single situation, but I am limiting myself to what I have observed practically. So, as we can see, the quadcopter, and I'll refer to UAVs now as quadcopters, they operate in three-dimensional space, as we have here, the X, Y, and Z axes. And therefore, they have 6 degrees of freedom. They could translate, meaning that they could move without rotation in either X, Y, or Z axis, as well as rotate in either or combination of these axes. So therefore, these 3 degrees of freedom translation, 3 degrees of freedom and rotation gives it a total of 6 degrees of freedom. Here I have just a little video, and I want you to note the direction of spin of the propellers. So let's see if we can get that. So as we are rotating that, you can see the direction of spin remains the same. And I'm sure that you have observed that if you go from, let's pause this. All right. If you go from one propeller to the next, there's always an opposite sense, S-E-N-S-E, right? So the sense of rotation, meaning that if this one spins clockwise, this one would spin anti-clockwise, and we go around the quadcopter like that. And that has to do with balance of something called torque. So just bear in mind, just very simply, once it's a quadcopter, all rotations are opposite to each other if you go around the quadcopter in a sequential fashion. Now, as promised, again, I need to get some space there. Just give me 1 second. Okay. As promised, I'm keeping this thing very short, and it's just going to help us to aid us in understanding how a quadcopter actually flies. So basically, it's just a little bit of physics. Now, in any flying device, you have 4 forces acting on it. The weight, which always acts downwards towards the earth. The thrust, which gives us the direction that the quadcopter will be flying in the upwards direction. The drag, which is, in this case, not opposite the thrust. In an aeroplane, it would be directly opposite the thrust, but this is opposite to the forward motion of the quadcopter. And then we have one more force, and that's the lift, which is directly opposite, or it's a vector opposing the weight. So I've just shown two motors here, and we've just put 2 forces, F1 and F3, but there are 4, as you rightly know. We have to mention some little things. So from Newton's second law, the quadcopter and all frames, reference frames on the Earth are inertial reference frames. So therefore, wherever the quadcopter flies, it's flying in an inertial reference frame, meaning that Newton's laws would hold in that reference frame. We know that the sum of the forces would be equal to the thrust. And I'm not going to go into any detail into this, but these are the equations for translation. And for hover, the quadcopter would be horizontal, and you'll see that T cos theta would balance W. And W is mg, which is mass by acceleration due to gravity. So basically, we'd have two forces in this case, along the z-axis and along the y-axis. Because I've not put in the other motors perpendicular to the plane, to this plane in the screen, I haven't considered the x translation. So that's it for that. Just take it that what I have here is correct, and it is. And the main point I'm trying to make here is that we are analyzing translation. So this has nothing to do with rotation. So the quadcopter has rotated to this point, and from that point onwards, it's translating. It's moving forward in a straight line direction, off to the right. Here, we look at the other force, the other mode of flying that the quadcopter could do. You would appreciate that in the z-axis, the quadcopter is able to go directly up and down without rotation. But in the x or y axes, if it has to move there, let's say x and y, it must rotate before it translates. Hence, we would write some similar equations. However, we're still applying Newton's law, but we're doing it for rotating bodies. So in this case, we'd have to make some assumptions that the quadcopter is a rigid body, meaning what? Meaning that external forces do not deform the shape of the object. So it's a rigid body, and when we apply rotating forces to it called torques, T-O-R-Q-U, right? T-O-R-Q-U-E-S, torques. When you apply a torque to it, it rotates. The whole body rotates. So I could do an analysis about the center of gravity of this, since the center of gravity would move just the same as any part of the quadcopter. And again, Newton's law in an inertial reference frame is used. So just like translation, we have now the sum of the torques is the moment of inertia by the rotational acceleration. And what I want you to get out of this is that once the quadcopter is rotating, there are two types of rotations that you can get. One, let's just see what we mean. You're going to rotate in this direction, right? So you can say that's the x-axis rotation. And then you can also get y-axis rotation. And you can also get z-axis rotation. So it can rotate about itself, basically, about its center of gravity. As well, it can rotate about the x and y axes. So there we have to do the torque analysis. And all I'm showing here, now this is a very, very simple, very super simple analysis. It's much more complicated than this. I'm just showing that from acceleration, looking for my pointer here, right? So from acceleration, we get a second order differential equal to a constant for now, right? And when we solve that, we see that the angle is very sensitive to time. So once this thing starts to rotate, it's going to start to rotate at a very high rate. There are 4 more forces that we have to look at, as well as the 4 motor torques. So we just leave that analysis there and give the general equations, and you have the net translation forces and the net torques. Here, M1, M2, and M3 would be the motor torques. This will be further taken in the next session, and we will do some analysis on this. And we can use the Newton-Euler equations in matrix form and solve some of these. Now, note carefully that we are only doing a physical analysis here. The quadcopter flies also by electronics. And just to mention, those would have to deal with control theory. So PID control, proportional, integral, and derivative control. So that's a whole other aspect. Actually, it's in one of the courses that we propose to start. Hopefully it gets off the ground. I've just put the lift equation here. this is what airplanes use, this is what NASA uses, and so on, to show that the force of lift is equal to some constant, which is determined by experiment. The density of the air, the area of the surface that is being lifted, and the velocity of the surface that is being lifted also. So this will have to come into play if you have some kind of wind resistance. It would modify your lift. Another thing I wanted to point out here, you see in this thing looking like a multiplication sign. That's not a multiplication sign. So these are vectors, L1 and F1. And with vectors, you have two types. You have scalar and vector multiplication. So scalar is the dot product, and this is the cross product. So if I say here L1, I don't say by, right? So it's not L1 multiplied by F1, it's L1 cross F1. So this is a vector product. It produces a force in a direction perpendicular to both of these. So that has to do with torque. Okay, the plus sign here means the regular plus, right? It's just the thing that looks like multiply. That's a cross vector product. Currently, we are not teaching that type of mathematics, so I hope that we will soon. All right, so let's see what actually happened. Let's see what actually happened to me. So you'll see I have a very small quadcopter. Let's look. All right, so as you can see, it fell out of the air. And it's not too much different from what happened in the start, where the quadcopter started to lift. It went into air traffic space and then decided to head for the Earth. My one tumbled. And I was asking the question, why is this happening? And so to answer that question, we have to look at data. The quadcopter itself has an EPROM, right? Erasable programming memory, which records sensor data. And a lot of sensors are put on it that it can record. You can retrieve it after a crash to determine what had happened. So initially, I'll speak of that after we look at these graphs. Initially, the quadcopter was not going into failsafe. So we had to make a modification to get it to go into failsafe. And now is the time to say what failsafe is. Failsafe is a procedure that any autonomous vehicle would go through in order to restore it back to a safe condition or a safe landing spot in the event of a failure. It can be many things that fail, and you'll see we'll be talking about radio failsafe. So let's look at this. Here we have 4 plots, and these plots are graphs of the motor speeds, right? So the current is directly proportional to the speed, so really it's a plot of the motor current, or the percentage that the motor is on. The main point to note here, the motors are tracking very well. There's very little noise on it, so it couldn't have been a problem with the motor. These lines here, you see them in packets, right? Little squares, 1, 2, 3. These are our magnetometer readings. The magnetometer is really just an electronic compass. As you can see, they are tracking pretty good. And because of the rotation of the quadcopter, they will change. And there's no noise really on that signal. So we'll eliminate that. I want to draw your attention to this line, which seems to be stepping down, the red line. And it starts from 1 and goes straight down to 0. This is what you call an RSSI signal. It's a received signal strength indicator. So this is my feedback to know if my signal is getting to my quadcopter. Of course, it starts high because the step-in fashion is because the data is sent in packets and it goes to 0. So at some point in time, this quadcopter was not receiving signal. It was not anything that I did, because this is my control graph and you can see nothing very strange here. But yet, the quadcopter stopped receiving signal and it automatically switched itself into failsafe mode, as you can see here, right? So it went into failsafe, return to home. However, as we saw, it did not return to home. So basically things are good here and things looking kind of, why is this happening? Let's compare another graph. And obviously here, you can see a great difference. You can see significant noise on the motor, right? That's interfering with the flight controller. Here you see some strange dip. Then the motors actually dip. It recovers. It goes along fairly well after that. Look at our magnetometer signal. It's all over the place. Again, look at our RSSI signal. It goes to 0. This is a strange phenomenon here. We did not send the signal, this dip. But basically, you're seeing the same thing happening. It lost signal. It tried to return to home, but it failed. It failed to reach. So the failsafe did initiate, and I'll tell you in the next slide what we did to get the failsafe initiated. All right, so basically the drone is controlled from the ground with a radio controller, a transmitter. There's a receiver and a control device called the flight controller on board the drone. It would fly normally. If it loses signal, then it's not supposed to crash and damage anybody. It's just supposed to go into failsafe and come back to its original home position. Right, so let's change that slide. Just a very, very little thing. That's probably a half a minute or less. The signals that we use are called spread spectrum signals. And it takes a narrow band. So what we have here is amplitude against frequency. It takes a narrow band signal. It applies some algorithm to it, which then spreads the signal. It has the same power, so the amplitude decreases, but spreads along more frequencies. There are two ways to do it: frequency hopping spread spectrum and direct sequence spread spectrum. So your routers and so on would be using this one, DSSS. It's not so, it's easy to break. It's easy to give interference on this one. The ones that we fly with would be the FHSS. And there's also SFHSS, which means secure frequency hopping. These are not so easy to give interference. So if we are proposing that while we were flying, there was some interference from some other device or some other phenomena that caused interference, then that would be a very long shot type of thing to say that it was sending our quadcopter into failsafe. Because these things are while there's no perfect system, these things are very good at filtering out narrowband interferences, and they do not interfere with each other. These are all digital. Long ago, just by note, long ago, we used to fly with FM, right? So it had a 72 megahertz signal, and you fly an airplane, etc. with FM. That's long gone. Too much interference. So the thing we just described there was radio failsafe. So what is radio failsafe? When your quadcopter loses signal and it is no longer in contact with the ground station signal, that's radio failsafe. Radio failsafe could happen either by the radio malfunctioning, the quadcopter receiver malfunctioning, or you go behind some object which prevents the signal from getting to it. Or, in the worst case, you fly out of range of the signal. Most off-the-shelf receivers would give you at least 1 mile in any direction. So vertically, you should supposed to get 1 mile control. So this was the problem. We had an Sbus problem. Sbus means serial bus. And why I'm not going into much detail is because I don't want to duplicate in a conference what's on the paper, because that will be automatic duplication. So I'll talk about it, but the rest of it is on the paper. So the pulse width modulated signal goes between 1,000 and 2,000 microseconds. The software that we used was INAV software, and the default to go into failsafe was set for 885 microseconds. The software, the Sbus converter that we use could not, in addition to the receiver, could not give us 885 microseconds. The lowest it was going was 900 microseconds. So we did a few experimental runs where we tried to keep below 1000 and above 900, because 900 was cutting it too close. The most optimized value that we found was 932 microseconds. That worked. That gave us our system going into failsafe previously when it was not. But as I will explain later, there were some problems. So let's just watch and see a successful run. This I have flight controller. I have programmer. It was going into failsafe, and now with some changes on the command line programming, we are now able to get it to go into failsafe, and with automatic autonomous return home. The blue signal readers or waiters at the home. Let's see how it goes. Okay, radio, I wanted to watch it. So I'm switching off the radio. All right, it's in failsafe. The radio off. You have the radio on the up? Okay. I hope it can come on box because the radio off. Okay, that's the same thing. The radio is still off. Successful, the radio is still off, right? So all the changes were successful. So see that it was successful, the changes on the important on it because I know you can't hear and see the same thing. All the time. Okay, so what I demonstrated was a successful failsafe initiation. Remember, this software was not going into failsafe before. We made some changes in the command line interface, command COMMAND, the command line interface, and we were able to get it into failsafe. I'm sure, I don't know how many noticed, but you saw the drop, right? It's not so, when it turned to come back to return to home, it actually dropped and then recovered and then came back to home. Actually, the GPS, so this here is the GPS and magnetometer system, right? It has to be away from magnetic fields. Okay, so I don't know if somebody wanted to say something, but okay, so I'm nearly finished. So that's what we achieved. The thing is, after that, we started to get, every single time we sent it up, we started to get crashes. And this is a very expensive cycle. We have to change parts. We have to change parts. I have to wait on parts, purchase the parts, wait on parts, put it on, then go back. If it crashes, then I have to repeat that cycle. And so that keeps the thing going. It's a lengthy process. I just wanted to show you very quickly. Let me see if I can change my share here. So I'm not sure. I'm not sure. I'm just trying to get. All right. So maybe I can do it this way. This is the GPS system, right? And this here, this thing that is smaller than my fingernail, I'm not sure if you've seen it properly. That's the compass, right? It's a magnetoresistive device. I have to use my microscope to change one of these. The problem here now is that you have, well, I wouldn't say fake chips, but okay, I don't know if you've seen that. That's one. On the I2C bus, they don't have the same addresses. And so the market is flooded with a lot of fake chips. Just to show you that this was our device, right? It's down for repairs now because it has crashed many times. So we're still in the process of trying to see how to regularize the system. We have made, as you can see, we have made some success. We have gotten some success. We have, let's go to the next slide. So we have partially answered the problem question, right? Why it wasn't going into Failsafe. We got that part done. But after getting it to work, at every point after that, and that was the only success we had. It's a good thing that I had it on camera. Every point after that, we had crashes. And I'm in the process of analyzing the black box data. I'm waiting on parts. I'm going to change things and see what happens then. So the work is to be continued. As a side note, when we fly, we have a limit of 400 feet in any direction, especially vertically. We have a common understanding with the Civil Aviation Authority in our country. We did send out a NOTAM, a notice to MN, so that they are aware that we fly on certain days at certain times. And when the airplanes are coming in, especially the commercial jets, they fly around us. So we have, we don't have to worry about that. And we shouldn't get into any trouble. So I want to thank UCC for this forum. It's an excellent forum. It's a good thing. I like it. I'm glad that I could have participated in it. I want to mention especially Dr. Naja. I put my email address here so that even if you think of a question or a comment after, at any point in time, I'm still here at UCC, and hopefully we'll be here for a while. You can always email me, and I'll try to see your questions and your comments. Very much appreciated. The video that you saw in the start, given the credit here, this was taken from YouTube. That's a very, very expensive quadcopter. It's a DJI, and they're probably like $5,000 US now. It happens to them. It happens to us. So we're still in the process of trying to figure out what's going on. So thanks a lot. I'll hand back over to the Master of Ceremonies now. Thank you. Rachel?
Thank you so much, Dr. Ramsaroop.
Thanks, Dr. Dawkins.
We are open for comments and questions, colleagues, and you don't have to understand the physics.
Well, I have my first question. You gotta wait on me, okay?
Yes, boss. Yes, boss. That's fine.
I like that.
Dr.
Yes,
Ramsaroop,
Yeah.
you lost me, I kind of get the gist of it. But see that physics? That
Well-
physics thing will tie me up.
Well, that's why I tried,
When you started code and scene, I was like, okay, all right, I'm gone. I'm out of this discussion. But seriously, just using the model of flight, I think brings home something in real life for students.
Correct.
And I think that will really help them to understand, to look beyond the complexity of the physics itself.
Correct.
Try to make the connection to a real life situation. So I just want to commend you on doing it that way.
Excellent, excellent. I was guided, I was planning to do little physics, but Dr. Dawkins brought it home, and she does have a point. So
Yeah.
I appreciate your comment, Doc, and it's something great that you said that we want to bring it over to our students. So let's hope it does happen.
Yeah.
Great, thank you.
Appreciate it.
Dr. Duquoy, you go now.
That's all.
Thank you, Your Majesty. Hello, everyone. Good afternoon. And I want to congratulate Dr. Ramsaroop on a very, very unique contribution to research. You have a very good template in the manufacture of toys or devices that will definitely appeal to everyone at all ages. I have an interest in both quantitative and qualitative types of research. So while your presentation was chiefly quantitative, I have a qualitative interest question. What will you say is your best personal takeaway from this work? Congratulations, and I listen.
I appreciate it. Oh, Dr. Ducour and everyone else, these are not toys. So yes, while it might have a good impact on toys, these are what you call hobby grade devices, right? And they can cause serious physical harm, physical body harm, even death to participants or pilots. That has been recorded already. So there is a significant danger. For example, I'm getting to your question. For example, when we fly, we don't allow anybody in the near vicinity, just in case of mishaps. And you saw the quadcopter fall in there. If it had fell on somebody, if children were there, or even big people, they would get some damage. Right. So let me see. I find that's a hard question, but nevertheless, let me give it a go. The takeaway from this is that the DJI thing, which is sold for a very high price, which has a brand name, and my home-built quadcopter, my scratch-built one, which you just saw, suffering from basically the same problem. The first guy lost his. Well, I didn't lose mine, but I lost a lot of components. And Failsafe, as I started, self-driving cars, robots, even NASA spacecraft. I think I saw the Chinese spacecraft. The solar cells are not generating electricity. And even these quadcopters, they suffer from problems. And it could be problems in the software, as well as it could be unforeseen problems, atmospheric conditions, and so on. So just to sum it up, the takeaway is that there's a lot more that we have to learn. There's a lot more research that we have to do. So thanks a lot for your question. Hope I answered it.
Thank you, Dr. Ramsaroop. But there's no doubt that the same mechanism, the same idea, the same knowledge can be transferred to the creation of toys for children, that's all? Am I wrong?
Thank you. Dr. Beverly Forrest Hines, I see your hand.
Yes, hi.
My email
Hi, good afternoon, everyone.
Good day, Dr. Hines.
Hi, Dr. Ramsaroop, very interesting presentation. And I think what you said at the end there, because I was trying to identify very quickly the significance of the work that you're doing. And I think your final response there cleared it up, right? Because as you said, your homegrown model and the very expensive model have like the same issues. So if it is you can solve the issue as and bring that to reality, then you have something there that to me could be like an income earner. And that will be very valuable to people. So I was looking and you answered it. Yeah. As to why.
But
so thank you.
I appreciate your comment. I'll say we, right? We are a good way off from that. I'll tell you why. For one thing, the satellites that civilians are allowed to use do not have very good spatial accuracy. So we have to recognize that there are satellites that the military use and satellites that civilians use. And part of the problem, maybe the solution too, is that DJI even though it's a brand name company, would be limited to the civilian use of GPS. The military, they alone have access to the more accurate GPS. So that could be part of the problem. We have no control over that. There are a lot more satellites in the sky now. So the American system is GPS, Global Positioning System. The Russian system is GLONASS. The Chinese system is BeiDou, and they have BeiDou 1, 2, I don't know if they have 3 now, supposed to be more accurate. And all of our receivers supposed to be able to intercept those signals. However, my personal experience right here in Trinidad is that when it works good. As you can see, the quadcopter came back to almost the same position it took off from. When it doesn't work, that's where the problem is. And yeah, we're still trying to find out. We keep pushing forward. So I thank you for your comment. Again, any questions, comments?
Any other questions, colleagues?
Okay, let me take this opportunity to ask one more. What's next in line?
Your hands up.
Yeah.
Oh, sorry.
Oh, Dr. Naja, great to see you. All right, let me answer Dr. Duqua's question first. Next in line. Well, I had hoped, I still hope, but I had hoped to present 3 of these this year. So spaced maybe a little bit equally. I'm not sure how the time is going to run. So what I had proposed for the next time, undoubtedly it will have to get into physics and mathematics, is to look at the solutions to these equations, look a little more in detail at black box data, and try to see definitely what our problem is, because there's that uncertain drop which I have been seeing. I cannot detect why. It's probably a power problem. I'm not getting power glitches when I analyze it. So there are some problems. So that's what I propose to do, at least for the next one.
Thanks for your response. Let me give way to His Majesty, Dr. Ndaja. Congratulations, Dr. Ndaja.
Dr. Naja?
Yes, Dr. Ramsaroop, can you hear me?
Yes, sir, I can hear you.
Yeah, I just want to know what frequency band was used in the communication channel.
Okay, so these, when I went through the signals, it's the 2.4 gigahertz signal frequency band, but remember it's spread spectrum. So this is what you call the ISM band, right? So medical devices use it, hobbyists use it, home systems use it. That's the license-free band. And that band combined with spread spectrum technology is supposed to be interference-free. So it wasn't really a problem of interference for us. It was just loss of signal for some reason.
All right, thank you.
Yes, Doc, thanks. There's somebody else?
Yes, somebody else who speaks the language. Somebody else who speaks the language.
That's science to science, yeah.
Dr. Peter, answer my chat question, please. And welcome, Mr. Fagan. Please,
there's a chat.
Please make your contribution.
All right, thank you, and good afternoon, everybody. Thank you for the presentation, Doc. It was very interesting. You reminded me of some work I'd done previously with Digicel. And when you mentioned the whole thing about frequency hopping, and then Dr. Ndaja asked a question about the spectrum, and it got me thinking, could it be related to interference? Because I know that a lot of devices operate in that band. So you have the point-to-point Wi-Fi, you have some domestic appliances that also operate in that band. And so, my question was, even though we have the frequency hopping, the sequence of that hopping and the number of other devices operating in that spectrum might have had some influence on the outcome. I don't know how much of an influence, but I was thinking along that line.
Okay, so yes, that is always a possibility. Well, I didn't mention it here, but when we suspected that it might have been interference, I went with a spectrometer and checked. And yes, there are signals there, right? And I tried to triangulate the position, and it was coming from one of the government buildings. However, it was in another frequency band, 6.4 gigahertz. So the chances, I mean, you fly these things and then you have the video signal that's at 5.8 gigahertz right next to the receiver, and there's no interference between them. So it's probably not interference. It certainly wouldn't be the cell phone towers, because they would send their signals on TDMA or CDMA, and that's another type of system, another multiplexing system. The chances of interference would be very, very small. However, something did happen, which we cannot put our hands on. And the last time this device crashed, it was just about 2 feet from me. So what interference, 2 feet, all right, let's say 2 feet from the transmitter. So what interference would be so strong as to be stronger than the transmitter at 2 feet? So yes, while that is a very valuable insight, I believe in our case, it is not the problem. So it's something to look at too. Thanks a lot.
Yeah, no problem, Doc. And you know what? Let me tell you why I was thinking along that line, though. Is that, would you say that each time you've done it, the result has been the same, or it has changed, and which would indicate that there's something changing to that outcome?
Okay, so we've done it on test conditions, basically at 2 different fields. And after that first success, the general result was the same, meaning yes, it did crash. The way it crashed, one case it started to turn and then just fell. Another case, it made the full turn, started to come back, and then fell. So I see a point. If it was the same thing, it did a halfway turn and fell, then yeah, something is common. But seeing that and nothing changed with the motors, with the propellers, etc., and you had this this different type of performance. So that's what we're actually looking at right now. We're trying to see if we could get some commonality, if there's some change that we could make to get this thing to behave the way it's supposed to behave. But it did start when we made that change on the software. So right now, my thought, and it's just a thought, I don't have a real proof for it, but it's what I've been saying. It seems as though the software is indicating something on the GUI, but something else is happening in the background. It seems so. Cannot prove it as yet. The software is being updated very often now.
Thanks, Doc.
Thanks a lot for your question. More questions or comments, anything?
Any other questions, folks? Well, hearing none, Dr. Jockey just stepped out for a hot minute. Let's just thank everyone for joining today. Rachel, is there anything else that we need to do?
I don't believe so.
Don't believe so? Okay. So let's thank everybody. And here's President again coming back to say hi and bye.
Good afternoon and thanks again. So grateful. Have a blessed weekend.
Thanks a lot.
I'm very, very grateful. Very grateful. Dr. Dawkins is here with me.
All right.
Yes.
Okay.
Same to you. Bye for now.
Well, have a pleasant weekend.
Thank you
All
all. Thank you
Same
so
to
much,
you.
Dr. Ramsaroop.
Thanks a lot. Appreciate it.
Thank you for really stimulating our senses and our brains
I
for the
appreciate it.
start of the year.
Sure.
So you
Have a
good
great
weekend.
weekend, everyone. Bye bye.
Bye-bye.
Bye, everybody. Take care. Keep good.
Bye, everyone.
Bye-bye.
Bye, everyone.
Bye-bye.